Hello. Welcome back to Chem 121. We'll wind this down here. We're going to continue on Chapter 8 today. We'll probably finish Chapter 8. What else do we have going on here? Let's see. Quiz number 7 is due next week. Lab worksheet number 4. We're going to talk really briefly about lab worksheet number 4. I really don't have much to say about it. So let me just put this on the screen and then let me capture this window. Boop. So same deal as always. There are some videos that I do want you to watch. Let me click down here. So if I click on this, I'm gonna do it this way, unfortunately. So this experiment has 2 parts to it. When you click on the videos link, you will get to this. The first one is for the dialysis part of the experiment. Dialysis is something that is very important in the medical profession. If you are working with people who have kidney issues, you often have to do blood dialysis, which is the removal of solutes. Normally, the kidneys are supposed to do that for you. However, when people suffer kidney failure, they become unable to do that. And if they accrue large concentrations of things like solute in their bloodstream, that can be very, very bad. So dialysis is not a very complex procedure in terms of the science behind it. So this experiment shows you how that works. It's basically, I can move stuff from a high concentration to a low concentration through a semi-permeable membrane. So you're going to see an experiment where they do this with a dialysis bag with a little bit of honey inside, and then you put that into a sample of water, and then you test the water to see if honey actually is in there, if it passed through the bag. The other 2 videos are about radiation. The first one is an actual demonstration of radiation on a Geiger counter in terms of things like distance and materials that it can penetrate through. We would actually have had you do this in the laboratory if we were able to. So this is the best approximation of that experiment that I could find on a video, and it's actually quite good. The third video is a description of half-life and what that means in terms of radioactive decay. An element has a half-life, which is how long it lasts for half of a sample to radioactively decay away. And the demonstration that he's going to do is he's going to cut a bunch of pieces of straws and then shake a box, and then all the ones that land in a certain orientation he's going to remove, and you can calculate the half-life that way. Then he's going to change a property about the straws, and you notice that the half-life changes completely. And it's really kind of cool to see him do that. Yeah, so please watch those videos. The lab is more or less just answer all of the questions about it. Let's see here. So where's the Google Sheet? So yeah, you're going to have a bunch of questions to answer, and there's a bunch of tabs. Make sure you are answering all the questions on all the tabs. And it directs you to go to the next tab at the bottom of each one, just so you don't miss it. So there you go. All right. So another one of those, please watch the video and then answer the questions types of worksheets. These topics we don't really get a chance to explore in this class because, one, they're not super chemistry related. Dialysis is more of a physics thing. We very briefly mention it when we talk about osmosis, which we'll get to today. But yeah, so let me know if you have any questions about that. On the screen, I have the problems that we left off on yesterday. I said that we would start with these. Now, if you've already done them, then hooray, you get to hang out for a bit. I'm going to give a few minutes, like 5 minutes or so, for anybody who wants to try to do these, and then we'll go over the answers together in just a bit. So please go ahead and do them if you didn't finish them yesterday or didn't do them overnight. 1 or 2 more minutes. We'll go over the answers. Sorry about that. I received a very important email that I had to address immediately, of course. All right, let's go over the answers here. So the first one is a mass percent. And hopefully we recall the formula for mass percent. Oops, why am I not writing? There we go. Mass percent is mass solute over mass solution times 100%. So I know that the mass of the solute is AgNO3, and that is 2.13 grams. I also know that the solvent is water, and I have 30 grams of that too. The solution is both of them added together, so we'll add them together, taking into account sig figs. And now I can enter the numbers in, so 32.1 goes there, 2.13 goes there. So that's going to be the mass percentage of silver nitrate in the solution. I got to find the calculator. There we go. And times 100, and I got 6.64%. And this is AgNO3, and this is mass. For the second one here, what is the mass volume percent if 100 grams of sodium nitrate are dissolved in water to make 1,250 milliliters of solution? So the volume percentage, or mass volume percentage formula, is mass of solute, specifically in grams, divided by the volume of the solution, specifically in milliliters, times 100%. And so we just enter in the numbers here. 100.0 grams divided by the volume in milliliters, which we've already given you. And then the units just kind of mysteriously go away. For mass volume. Because we don't want to deal with them. So I get 100 over 1250 times 100%. I get an 8% solution. Specifically 8.00 for sig figs. And this is NaNO3 MV. And I'll just homework practice there. That's fine. All right. Finally, what is the molarity of solution prepared from 25 grams of sugar? This is glucose. Mixed with water to form 1.50 liters of solution. This could be for like therapy or something. Now, to do molarity, we need to know the number of moles of solute. And then we need to know the number of liters of the solution. So to get the number of moles of solute, we have a mass of solute. And we need to turn that into moles. And we do that by looking up the molar mass. So 1 mole of C6H12O6 is... Do I still have Lentec open? I do. Okay, C6H12O6. 180.16 grams. So the number of moles that is 0.139 moles of this, C6H12O6. So that's going to be the moles of solute. But now I need the liters of solution. So what I'm going to do is I'm going to just take this number and I'm going to divide it right here. and I have 1.50 liters of solution. So the molarity of this solution is just that divided by 1.50, and I get 0.0925 moles per liter. Or I could have just written capital M instead of moles per liter. Either one works. So please be able to do these types of calculations for this section. We're going to use these concentration numbers in the next section, which is coming up in just a second here. Dilution. Now, dilution is a very important procedure to follow. The reason being, if I wanted to give you an IV, I would hang like a liter bag or so on the little hook and then put the IV needle in and then give that to you. But where would I get the bag from? Presumably, I would get it from the stock room or storage. Well, IV bags, if they're all a liter and I have to give out like thousands of them a day, that's going to take up a lot of space, right? Like, you could have an entire room just dedicated to IV bags. Or you can make them on the fly, but then you need to keep that solution somewhere, right? And so if you're imagining like this giant vat where like IV solution is just like dispensed, some issues with that. One is that's really big, and two, probably not very sanitary if it's very large, right? So what's a better way to do this? Well, what if I gave you a solution that was much, much more concentrated? For instance, like most of the water had not been added. You could supply the water yourself, right? Then I can give you something that's 1,000 times more concentrated and has 1,000 times less volume. So we're not shipping water around when there's already water at the place that the hospital is at, right? So dilution is a strategy to get around some of these logistical problems that would otherwise come up by transporting large quantities of solutions that are just very dilute, right? So you can prepare your own IV bag from a quantity of saline solution that has already been made for you. Now, I do realize that this is kind of a weird example because for saline solution, you could literally just add salt to water and get a really close approximation. So we're not, you don't even need to have any water. You can just sell the salt or get salt from a specific supplier that is medical grade or whatever. But in the event that you are using a solution that could not be sold as a solid, this is the sort of operation that you would take in order to prepare solutions in the laboratory. So here's how this works. If you have a solution that's concentrated and you want to get its concentration to be less than what it was before, you can do that by simply adding water. Oops. So what ends up happening is, okay, so let me draw a picture here. So let's suppose that I have this solution and I have this much solute with this red line in here. So this is concentrated. If I were to add water to it to double its volume, then what would end up happening is I would have twice the volume, but the same amount of solute. So that line that I have is now spread out over the entire thing, and it's a lot less concentrated. As you can tell by there's less ink per unit area. Like if I was drawing dots, for example, maybe I should just draw dots. Oops. So here's my solution. I'm going to put 20 dots in each one. And then I'm going to put 20 dots over here. And you can tell that in the dilute solution, they're way more spread out. So if I took 10 milliliters of the one on the right, I would get less dots than if I took 10 milliliters of the one on the left. I have diluted the solution. Now the formula for dilution is just this. That's a very simple formula. However, there are a lot of parts in there and a lot of letters, and we need to actually identify what they are. So the first thing I'm going to do is I'm going to just draw a line down the middle. And on the left, I'm going to write stock. And on the right, I'm going to write dilute, although I'm going to misspell it. So there you go. So S is stock and D is dilute. Now, what can we do with this C and this V? So C is concentration. And typically we're going to use moles per liter, although you could use whatever concentration unit you wanted to. V is volume. And the volume can be whatever you want it to be as well, but it has to be the same on both sides. So in other words, CS is the concentration of the stock solution. In other words, that's the concentration we have in the bottle that we have. It's too concentrated, though. We need to dilute that. VS is going to be the volume used of this solution. So we're going to add some amount of this to a beaker or a flask or whatever. And then we're going to add water to that. But before we add water to it, we need to measure out some quantity. And the calculation and our procedure will determine how much we weigh out or measure out. All right. On the other side, CD is the dilute concentration. Now, we get to choose what the dilute concentration is. You get to say what it is. If a procedure asks you, hey, you need to make this solution, that would be your dilute concentration. That's what you want to make. When you are done, you should have some solution of this concentration. And then VD, the dilute volume, is how much of the solution you're going to make. So you get to choose these two, usually. Or a procedure will choose them for you, and then you carry out the motions. Now, in most cases, you get to choose these, so they are known. And you don't get to choose this one, but it's printed on the bottle. So it's fixed and you can't adjust it. That means that you end up solving this expression for this number. How much of the stock solution is needed to prepare the dilute one? And then once you solve for the volume, you then do the procedure. Okay, I pour out whatever volume I measured or calculated. I put it in a container that is as big as I want it to be. And I add enough water to fill that container so that I have the concentration I was looking for. That's the gist of it. So let's do a practice example. These are just descriptions of what those terms are, which we just did. And again, most of the time you're going to solve for VS, not always. But conceptually, you can solve for any term here. Practically, VS is the one that you will solve for. So let's do an example here. Let me get this captured in the window. So I have 4 molar HCl in the stockroom, But I want 100 milliliters of 0.05 molar HCl. So I want something way more dilute, because 4 molar HCl is too concentrated. It might ruin my experiment. So I want to describe how to dilute this solution. So first, let's write the dilution formula. And here's what I do. I write stock, dilute, concentration, volume. And I make a little chart. Kind of like how I made the little pressure and temperature charts and volume charts for the gas laws. I do the same thing here. So let's look at the numbers. So let's start with the stock concentration, CS. Which of those is the stockroom concentration? Well, there's two concentrations. They have molarity. And the stockroom one has to be bigger because we're diluting that, right? So the stock concentration in this problem must be 4.00 molar HCl. The dilute concentration must be the other one. So there we go. We've eliminated two of the three numbers in the problem. From the paragraph, we can now just place the last one. I need 100 milliliters of the dilute solution. So we could just write that in here. The other thing that's left over must be what we solve for. So let's solve for it. So we'll divide both sides by CS to get that. And then I just plug in the numbers. CD, VD, and CS. Now remember, I said that you can use any units you want to, as long as they are the same. So if this is in milliliters, this will end up in milliliters. You could see that because that's the unit that's left over, right? So we'll punch that in the calculator. 0.05 times 100 divided by 4. And I got 1.25 milliliters. Okay, I got a number, but what does this mean? So this is what my volume of stock solution is. Let me leave the calculation on there in case you need it. Now, getting the number is not really all there is to the process, because the question is asking you how to describe how to dilute the solution. Just writing a number doesn't do that, right? So you need to make the procedure in this problem, and here's how we'll do that. So to make the solution, you're going to do the following 3 steps. The first step is to measure. You're going to add some amount of the stock solution, and then we'll write what that is, to some volume flask or container. Now we need to fill in all of this stuff. So how much stock solution did we measure? Well, we just calculated that, right? What is the stock solution? Well, we know that because we just put that in the chart. That was this, right? And then we'll just write HCl because we want to identify it. How much do I want to make? I want to make 100 milliliters. So in other words, for our little template here, I added VS milliliters of stock solution, which was CS, to a volume flask, which we know. So that's step 1. Step 2 is to dilute. And all you have to do is write this. Add enough H2O to the fill line. Do you need to measure out 100 milliliters of water? No, because remember, volumes don't add. We're going to just add some amount of water. You don't even need to measure the amount of water out. Just pour it right into the flask until you have reached the fill line. Once you have done that, you will have 100 milliliters of solution. Step 3 is simply just mix it really well. If you don't mix it, then all your solutes at the bottom, all your water's at the top, and then if you try to use it immediately, you get mostly water at the start, and that's no good. There is a secret 4th step. Enjoy. However, that's a secret, so you don't get to know about it. Wait. Oh, shit. I told you the secret, but that's okay. All right. So that's how you make any solution. You basically follow this template. The first thing you need to do is solve for the amount that you need. That's this right here. Use the problem to fill in the remaining numbers. Once you know the volume that you need of your stock solution, you can use this as a template. Measure out the amount you calculated of the stock solution, write down what it is, and put it in a flask of whatever volume you need, VD. Then dilute it with enough water and mix it really well, and you're all set. And I revealed the secret again. Look at this. Whatever, it's out now. So, all right. I think you could do it. All right. So we're just showing that calculation here. So what I want you to do is I want you to make these solutions. Now, you don't have really that much time to do all of them, but do as many of these solutions as you can. So I'm going to give you 4 molar HCl. And what I want you to do is I want you to make 25 milliliters of 1 molar HCl, 250 milliliters of 2 molar HCl, and then 1,000 milliliters of 0.0250 molar HCl. Okay. Do these 3 solutions separately. Don't do them all in the same calculation. Do the first calculation through, write out the procedure for it, do the second one, write out its procedure, and so on. Type anything you'd like in the chat to let me know how you're doing. We'll go over the answers in about 5 or 6 minutes. 2 more minutes. We'll go over the answers here. All right, let's go over the answers here. So we're going to do the same procedure each time. I'm only going to write it out once, though. Oh, wrong color. Hold on. All right, so for the first solution, they're all going to be 4 molar HCl. When I'm done diluting it, it'll be 1 molar, and I want 25 milliliters of it. So we'll solve the equation. So CD is 1, VD is 25, and CS is 4. Oops, wrote over my decimal point there. So when I do this calculation, I get VS is 6.25, which for sig figs, I have to round to 6.3. And then, so my procedure would be, so step 1, measure 6.3 milliliters of 4 molar HCl into a 25 ml flask. And then step 2 is add H2O to the calibration line. And then 3 is mix well. Oh, you can see that one, though, too. Okay. There you go. That's how you do it. For the next solution, we do the same thing. We just change all the numbers out. So let's edit. So I'm going to erase that and that. Oh, for fuck's sake. That. And that. There we go. Oh, what did I do? There we go. All right, so now I want 250 milliliters of a 2 molar solution. So we'll plug in the numbers. So I only get to keep 2 sig figs, so this is going to become... Why isn't this working? Oh, because I'm not hitting the... Oh, I am hitting the button. Oh, it's just not showing it. Weird. Okay. So we get that. And then our procedure basically just changes to like, boop. And then this is 250. And the rest remains the same. And then for the last one, there we go. Now I want 1,000 milliliters of 0.0250 molar HCl. And same procedure as before. And I can't do that one in my head. So 0.0250 times 1,000 divided by 4. And look at that, we get the same number as before for the first one. So our procedure will change slightly to that. And now we want to put this in a 1,000 milliliter flask, and that procedure is good for number 3. So you can see how this procedure is very useful in terms of a template. All you have to do is add the numbers in the correct spots, and you're all set. All right, that's dilutions. Let me know if you have any questions. When we come back, we're going to start talking about colligative properties, but it is time for a break. Oops. Oh, break is over. No, I'm just kidding. Boop, there we go. So I'll turn on the timer, and I'll get the music going, and we'll see you in just a little bit. All right, we're back. So these last two sections, we're not going to do any math in the rest of Chapter 8 here. We're just going to talk about some various properties of solutions that are actually not chemical in nature. These are all entirely physical properties. And as a result, these properties can be explained just by having the presence of particles. Their identity doesn't matter. So whether it's sodium or potassium or chloride or hydroxide or whatever, these specific properties don't care about that. They just care about the number of particles in the solution. So concentration matters, but what they are does not. We're going to call any property that follows those descriptors a colligative property. Colligative properties are only dependent on how much solute you have, not what it is. So no chemistry is happening here. These are the four colligative properties we're going to talk about. And a lot of these have really practical implications on things that you do all the time, believe it or not. And by all the time, I mean like frequently enough that like every year it happens. There's one major one that I'm thinking of, but it only happens in the winter. And it's when we put salt on the roads. Why is salt used on the roads to melt things? Well, it turns out that when you make a solution, its freezing point goes down. Now, when you make pasta and you add salt to your water, you actually increase its boiling point. That's not the main reason you do it, but it's just a side effect of that. Vapor pressure is important because maybe we don't want the solution to evaporate away, so you add substances to it. For instance, if you are storing a vehicle and you have all of your gas just in the engine, not in the engine, but in the fuel tank, you don't store the gas in the engine. That's not where it goes. If you store it just in the fuel tank, it will eventually evaporate away because you're not sealing the container completely shut. Like, it's not airtight. I mean, you try and get it as airtight as you can, but fumes can get out through various seals and whatever. So in order to reduce its ability to evaporate, you add a stabilizer to it, which changes its vapor pressure. And then finally, osmotic pressure is important for things like blood pressure and stuff like that. And we'll talk about all of these in these slides. Now, the first thing that we're going to consider is how many pieces does each unit of solute split into. So for instance, if I put in sugar, which is a covalent molecular compound, these form individual units, but they don't split up any further. So if I look at a sugar molecule and I put one sugar molecule in my solution, I end up with one particle. Because the sugar does not dissociate into all its C's and H's and O's. All those covalent bonds remain in place. However, if I had an ionic compound, ionic compounds split into particles. And that's going to depend on how many particles there are. In this example, sodium chloride splits into two pieces. There's the sodium piece and the chloride piece. So for each unit of NaCl I drop into the solution, I actually get two particles out. And since the number of particles is all that matters, if I put the same number of NaCl units in as I do sugar units, the sodium chloride is twice as effective. So let's do an example. Which of these substances is more impactful on colligative properties? CO2, which is molecular, or KBr, which is ionic. Tell me how many pieces each splits into, if any, and then tell me which one is more effective. Type your answers in the chat. There you go. That's the right answer. Very good. So CO2 is molecular. It doesn't split in any pieces. So it's only one particle. KBr splits into two pieces, so each unit gives you two particles. So it's twice as effective. How about this pair? Which is more effective? That's a little more challenging, so I'll give you a second to think about it. I'll give you a hint. Think about what charges each ion forms, and then just split it all into the pieces so that the charges balance. All right, let's go over the answer here. So if I'm going to split this into pieces, so I know that chloride in an ionic compound is always like this, so there must be two of them. Here's my calcium. So I have 3 particles. This one's a little harder because I've got these sodiums here. That one's not so bad. But what is this? Well, it turns out that this is just one particle on its own. This is phosphate. This splits into 4 particles, so 1 formula unit of sodium phosphate is more effective than 1 unit of calcium chloride because it makes more particles. There you go. Very good. All right. So counting the number of particles that something splits into is the important first step. Now, there are formulas that can be used to calculate how effective these are. They are well beyond the scope of this class. We do this in engineering chemistry, where we can calculate the vapor pressure and how much it's lowered by, what fraction occurs, and then we can calculate the freezing point depression and boiling point elevation. We're just going to talk about these effects. Now, when you add a solute to your solution, and the solute is non-volatile, what does non-volatile mean? Non-volatile means it doesn't evaporate. Now, an example of this would be like sodium chloride. Sodium chloride doesn't evaporate. It's non-volatile. Acetone would be an example of a volatile solute. Acetone does evaporate. So mixing acetone and water still produces colligative effects, but it will slowly evaporate too. When you add a non-volatile solute to the solvent, the vapor pressure goes down. And here's why. If this is the surface of my container, it's kind of hard to see from the sideways angle. Here's my solution. Here's the surface, and I'm going to do water in blue. some number of particles are going to evaporate from the surface because they are able to and they are there. But what if I put a non-volatile solute in here? Some amount of solute is going to occupy the surface spaces where water would normally be and try and evaporate. And anything that's coming out of those spaces can no longer evaporate. So this one can't, neither can that one or that one. I tried to choose them randomly and I did a poor job. So as I fill up the surface with non-volatile solute, I block off the surface from evaporation. Now, obviously, this is distributed through the entire solution, and I'm just talking about the very topmost layer here. But if I have a solution that's 10% non-volatile solute, 10% of the surface will be blocked. And so the vapor pressure should go down by 10%, and it totally does. Now, because lowering the vapor pressure means that stuff boils less effectively, remember, vapor pressure has to equal atmospheric pressure in order for boiling to occur. By adding solute to my solution, the boiling point is increased because I had to heat it that much more to get the vapor pressure up to what it needed to be. So as a consequence of this, boiling point increases when you add solute. Now, a really common place this is used is your automobile. If you put antifreeze in your radiator, the water can absorb more heat before it starts boiling. Now, if all the water boils away in your radiator, there's no more water for your engine to transmit heat to, and the engine overheats. This is really common with really, really old cars. I'm looking at my family friend's car that I grew up. They had this old truck that every single year we would go camping with them, and the truck would overheat the radiator as it drove up the mountain with the trailer behind it. And then we would have to sit there and wait for an hour while they put water in it, while it cooled off. And this happened 2 or 3 times along the trip. I made this trip 2 years ago. I drove down there myself. When I drove down to California, I went to this mountain that I went camping in as a kid. No problems with my Jeep. I went up the mountain. My engine temperature didn't even budge. It was a really fun trip, but holy crap, was it slow when you had to wait on a radiator. And you know what would have fixed this? Putting in some goddamn antifreeze. Because it increases the boiling point. The water can hold that much more heat, which might be just enough so that it doesn't boil away. Now you might think, well, wait a second, it's antifreeze. How does this help with boiling? Well, it also helps with freezing, it turns out, because when you add a solute, the freezing point of your solution goes down. And here's why. Freezing is the act of turning something from a liquid into a solid. And in order to be a solid, you need to have a very regular arrangement of molecules. But if you put shit in the way, like this non-volatile solute, which is right here, so here's my solute, and then the blue ones are water. If you put things in the way, the liquid or the solvent, water in this case, can't align in the orientations that it needs to form a solid. And the only way that you can then make it freeze is you have to cool it down even further so the molecules are slower and can freeze in some other way. Now, this is really useful for our purposes, not just in the engine block to keep your engine running, because your radiator can't just be a solid block of ice. That's no good. But neither can the road. The road can also not be a solid block of ice. You would have no traction, and then you would drive all over the place, and you'd lose control of your vehicle. So what we do is we add salts to the road. We add sodium chloride because it's abundant and cheap. When you add salt to the surface of the ice, the ice interacts with the solute, and it becomes a liquid again because the salt then disperses into the crystal structure of the ice and disrupts it, and it causes the ice to melt. Now, this is always going to help us unless it's extremely cold out, because the freezing point goes down, but it's not completely removed. So, for instance, adding enough salt to water can lower its freezing point by like 10 to 12 to 14 degrees Celsius. That's significant, but temperatures lower than negative 15 Celsius are possible. So if you're doing this in Canada, like in Nunavut or the Yukon territories, or like northern Alaska, all the salt in the world won't help you. At that point, you just have to chain up your tires and go real slow and hope for the best. All right, so those are 3 of the colligative properties we're going to discuss, but the last one's special. We're going to talk about it in its own section to close out the chapter today. And so this one's osmosis. Osmosis is a biological phenomenon that is very important because it involves the movement of water. If you've ever been dehydrated, which we're people and we don't drink enough water, right? Of course we've been dehydrated. How do you rehydrate? And the answer is you don't drink salt water or ocean water or things like that. And you might have wondered why. There's an old novel. It's called Life of Pi, and it's about a guy who's trapped on a boat on the ocean with like a tiger. And there's a famous line that goes, "Water, water everywhere, but not a drop to drink." And I think it's from that book. And the reason for that is because salt water contains lots of solute. And the presence of a solute will influence osmosis. And if you consume salt water, that can actually be deadly. It will lead to critical dehydration. And the reason for that is because of how osmosis behaves. First, let's talk about how things move. In biology, there are things that allow certain objects to go through freely and then restrict or constrain others. These are things that are called semi-permeable. So, for instance, your cells are all surrounded by cell membranes. Cell membranes are semi-permeable. We let water through specific channels, but other things are restricted. On the diagram below here, you can see the blue spheres can pass through the wall, and they can go in any direction that they want to, left or right. The green spheres, however, are too big, and so they get excluded. Now, as a result of this, if only one thing can move, then the water is going to move in one direction more than the other if the sides are not exactly the same. Now, what is the behavior of water? Here's how water works. So, water will move through a barrier that is semi-permeable, and it does so in this fashion. If the concentration is different on both sides, it moves to try and equalize it so that it's the same. You'll reach a state called equilibrium. We're going to talk about equilibrium next week. And that process is known as osmosis. Now, I don't remember if I have a picture here. I do have a picture here. Okay. So, osmosis is the movement of water through a membrane to equalize concentration on both sides. And yeah, there was definitely a movie about it. I've never seen the movie. I've actually never read the book, but it is a very famous book. And they actually included like a picture of the cover of the book in one of the chemistry texts they used to teach out of. So I just knew it from there. So here's how this works in terms of a visual. Let's suppose that in a solution, I have a semi-permeable membrane right here, and on the left, I have a concentrated solution. There's lots of solute. But on the right, I have a solution that's fairly dilute. There's not as many dots over there. In fact, they're a little too close. Let me move some out. There we go. Now, what's going to happen is that in order for me to make this concentration equal on both sides, by only moving water, I have to move water in the direction of the more concentrated solution. So my water is going to move this direction. And here's why it does that. We know that concentration is the number of particles, or moles, over its volume. Now, if I want this number to go down, but I can't adjust this number because it's fixed, I can't move solute through the barrier, my only option is to increase this number, because dividing by a bigger number would make the result smaller. So the net result is that water will move in this direction, and this volume will increase. When that happens, the number of solute particles is still the same over here, but they're spread out more. In fact, they're spread out the same amount as the stuff on the other side. When that happens, osmosis reaches equilibrium, and now the water will move through in both directions equally. Now, this does result in a very strange looking thing. You get this sort of column of water that's hovering over the rest of it. This is called osmotic pressure. And this is the force that osmosis exerts on surroundings due to the movement of water. A consequence of osmotic pressure is things like blood pressure. Your blood pressure is basically osmotic pressure. There are other factors that go into it. But you may have heard that if you have high blood pressure, you can't eat salt, or you need to reduce your sodium intake. I had an example of that today. I ate a lot of salt with my breakfast, and I was like, wow, that was way too salty. And then later I had like a headache. It's probably because my blood pressure was a little higher than it normally would be. Normally my blood pressure is actually really low. But if your blood pressure is high, that's because there are too many ions in your bloodstream because you consume too many sodium particles. And so what's happening is all the water is flowing out of cells and into your blood. And it increases the pressure of the blood on the artery walls. So osmotic pressure is actually very practical. Now, if you are a cell, you can be subject to osmotic pressure in both extremes. Too high and too low are both very bad. And if the blood pressure, or in this case osmotic pressure, is too high or too low, the cell can rupture. And we're going to look at some examples of that on this next screen. Now, I have pictures of these, but I always feel like drawing this out is more effective. So we're going to draw a cell. Here's our cell. And then out here is the bloodstream. Now, this cell could be a blood cell, or it could be like any cell on the wall of the artery, or whatever. It's just a cell. And the cell has water in it. So we're going to add water. We're going to put water everywhere. There's water inside the cell, and there's water outside the cell. But we don't really care so much about the water part. What we care about are the ions that are inside. Now, all cells and all bloodstreams have ions in them. So I'm going to represent the ions by just drawing this. And what I'm going to do is I'm going to then erase... Oh, I can't do it on here, so... You know, let's just get rid of the water here. We know that there's water here, because it's going to be hard to see the ions. Oh, Photoshop, stop it. There we go. That's close enough. There we go. We can get rid of that. All right. So I have ions in the cell. And I also have ions outside of the cell. If the concentration of ions is the same inside and outside, then water will move in and out at the same rate, and the cell membrane will remain the same size. Kind of like how the balloon that we showed in Chapter 7 with air pressure on the inside and the outside, if it's the same on both sides, that doesn't move, and the cell will remain intact. But let's suppose that you drank salt water. The salt water would be absorbed by your digestive tract and then transmit through your bloodstream. And so this would be the effect of that. So now you drank salt water. It's very, very salty. You've had way too much salt. What happens? Well, your blood pressure spikes because water is no longer going into the cell. Oops, I erased the wrong one there. Now all the water is going to try and come out of the cell because what it wants to do is make the concentration equal on both sides. So as a result, your cell will then shrivel up to try and increase the concentration inside and reduce the concentration of salt outside. And so the end result you get is dehydration. Now, the end result that this happens from a biological perspective is that your cells crenate. Crenation is the shriveling or dehydration of cells, and that's obviously bad. If your cells shrivel, they can't perform their function, and then your biological system can shut down, and that's obviously no good. So that's this first one here. Oh, we'll come back to osmolarity in a second. So that's this right here. Now, the term for the solutions that you consumed, the salt water in this case, is hypertonic. If you drink something hypertonic or you administer something hypertonic, so like a saline solution that you rinse your nasal passages for. This is a real popular thing to do, is you use like a neti pot, and if you put too much solute into the neti pot, it can be effective because it pulls more water out and then your sinuses will deflate. But if you do it too often, then you'll dry out your nasal passages, and that causes other problems. So a hypertonic solution has too much solute relative to your bloodstream, or your body, or your physiology, or whatever. All right, let's look at the other process. So I'm going to just put it on the screen real quick here, but then we're going to immediately go back to this. So let's erase everything here. We'll draw the cell again. And here's your bloodstream. And in your blood, or in your cells, are ions. And we'll try and make the same concentration out here. That looks about right. Now what we're going to do is we're going to drink way too much water. And what ends up happening here is that we dilute the bloodstream. Now, before, we had water going in and out when it was equal, but now all the water just wants to go in this direction. Because, oh, the concentration outside is too low. So I need to add water to the cell to increase its volume so that the concentration inside is the same. And what ends up happening now is your cell inflates like a balloon and can rupture. I'm trying to make little pop sounds. There we go. So if you have too much water in there, the cell will burst. And this physical or physiological process is called hemolysis. Hemolysis of a cell, or when cells hemolyze, they pop. Now, specifically, for blood cells. This is a concern. You do not want your blood cells to pop, because the things that are inside your blood cells should remain in the cells and not in your bloodstream, which would cause other problems. Now, the solution that is to dilute is hypotonic. So a hypotonic solution is too low of a concentration. So now, obviously, this is not something that you're going to run into by drinking like 8 glasses of water a day, because that's how much water you are losing due to evaporation and urination and respiration and stuff like that. However, if you were drinking like 16 or 24 glasses of water, you're like, I just love water, I can't stop drinking it. You could reach a point where you get water toxicity. I tell this story every time I talk about hemolysis. There was a contest a long time ago for when the Nintendo Wii came out in like 2003, 2004, around mid 2000s or something. Lots of people would have contests to give them away, and one such place had this contest that was called Hold Your Wii for a Wii. And the contest was drink as much water as you can without using the bathroom. And they chose a winner by some rubric. Well, somebody entered this contest in order to win this prize for their child or something like that, and she ended up passing away from the effects of having too much water in their system. Now, I actually spoke with a medical professional about this, because I would tell this story every time, and she told me, well, this is probably not why they died, because running out of sodium causes other problems. So diluting the sodium would get you first before the hemolysis would. But if your cells all hemolyze, that would be a very bad thing too. And that's definitely something that you would risk if you drank too much water. So, too much water, bad. Too little water, also bad. By the Goldilocks principle, there must be something that is just right, which is an isotonic solution. Now, what is an isotonic solution for the body? I have those numbers written on the screen here. And they are, for saline solution, isotonic is 0.9% mass volume NaCl. If you have ever had an IV bag, it will have this number printed on it somewhere. I actually have a student who gave me an IV bag so I could use it in a class demonstration, and I'd love to do that. It's currently in my office at Everett Community College, so I can't do that. But if you come and visit for some reason, I don't know why you would do this, hey, I want to see the IV bag, then sure, I'll show it to you. You could also just go to work, because you're probably going to be in the nursing profession anyway, and you will see these things all the time. Now, what if you don't want to use sodium chloride? What if you have other reasons to use other solutions? So, for example, if somebody is dehydrated and they're malnourished, for example, maybe they went hiking in the wilderness and were lost for like 7 or 8 days, and they didn't have any food. Well, you don't just need to rehydrate them. You also need to treat them for nourishment. And so for glucose, a 5% solution is isotonic with blood. So if you administer these solutions, 0.9% NaCl and 5% glucose, independently, don't put them together, you will attain an isotonic solution that can be used for safely hydrating a person. Because if they're dehydrated, it will slowly add water until they're at equilibrium. And if they are overhydrated, well, you wouldn't be giving them an IV anyway. And then the glucose can be used by cells for energy. So down at the bottom, you just have to compare these numbers. And the body is not this sensitive. So this number right here, this would be essentially isotonic. And so this would be safe. However, these other solutions are not the correct proportion. So 1.5 here is too concentrated. So it's hypertonic. And a hypertonic solution will lead to crenation. Likewise, this solution, 0.7, is hypotonic and will lead to hemolysis. I actually learned this the other day. Lysis is just the process by which cells burst or rupture. When you freeze things, the cells tend to break, which is why food gets squishy when you freeze it. And that's called lysing. Hemo is for blood, so I think this term might specifically be for blood cells. But if you're just curious, like, can I apply this to anything? Yeah. Lysis would just be the general term for general cells rupturing. Now I think about it, I might have been pronouncing hemolysis wrong all this time. I've always called it hemolysis, but whatever. This is not a grammar class. All right. I do have to scroll back a few slides because we did skip over one little bit of a topic real quick. Written on the side of the containers for IV bags is something that says osmolarity. What osmolarity is it is the molarity of whatever solution you're preparing multiplied by this coefficient I. I is the number of pieces the solution or the solute will split into. So for example, if we were making a saline solution, I would be 2 because sodium chloride would split into 2 pieces, the sodium part and the chloride part. Now, why do we care about osmolarity? The answer is that any solutions that have the same osmolarity will have the same osmotic pressure. So if I had a 1.5 molar sodium chloride solution, what would its osmolarity be? Well, it would be 1.5 times 2, or 3. Now, this is just a nice unit that we can use when preparing any solution that we want to. If I know the osmolarity of blood, which is written on the side of the IV bag, you can make any other solution you want to with the same osmolarity, and it will be isotonic. So that's why these numbers right here are different. Because glucose is a much heavier molecule than sodium chloride. So 5% mass by volume works out to be the same osmolarity as something that's 0.9% mass volume. And I could actually do the math for you, but I don't think you want to sit here and watch me do a calculation just to prove that it's true, when you could instead be done with the chapter and celebrate, and we'll just end class early, right? So there's the homework practice at the bottom. Now that we're at like the end of the quarter, so like the ends of these chapters, we actually get to start to talk about the biology stuff. And I'm not a biologist. I'm an inorganic chemist, so like I study all of these processes, but I don't know what they do on biology. But I've picked up some of it as I've gone, and it's actually really fascinating. So I hope that like as we get towards the end of the quarter here, that these last few chapters, like it all starts to kind of congeal together, and you can see, oh, this is why I'm taking this class after all. That makes sense. Because I can definitely see why around chapter 5 or 6 you're like, why the fuck am I required to take this as a nurse? And this is why, because we're getting to the part where it all starts to come together, and so you can actually see this in action. All right, there's your dancing orc. I don't know why it cut out there, but that's okay. We're done for the day. There's only about 4 more minutes in class, so we're not going to start chapter 9. This does mean that the quiz will go up, and you'll notice that you have a quiz due next week on Tuesday. There is going to be another quiz for week 8, or for chapter 8 added there. So quiz number 8. And it's going to be due the same day as your lab. So be very careful that you don't... Oops, I ran into my... let me just move the Metroid Prime here. be very careful about budgeting your time, because all of this stuff's going to sort of pile up towards the end here. So I'm going to go set that deadline for the quiz right after class is over. And speaking of class being over, it's over right now. I want to thank everyone for coming to the lecture today. Make sure you work on this stuff over the weekend. We'll see you next week for Chapter 9.